US Physics Olympiad, year 2017, USAPHO, final round. That was 2 parts for this round. First part was 4 problems A, and the second part was 2 problems B. For each part that was given 60 minutes. So if you want to see all these problems, please subscribe for this channel. Problem A1. A pair of wedges are located on a horizontal surface. The coefficient of friction, both sliding and static, between the wedges is nu. The coefficient of friction between the bottom wedge B and the horizontal surface is nu, and the angle of the wedge is theta. The mass of the top wedge A is m, and the mass of the bottom wedge B is 2m. A horizontal force F directed to the left is applied to the bottom wedge as shown in the figure. Determine the range of values for F so that the top wedge does not slip on the bottom wedge. Express your answers in terms of any of all of m, g, theta and mu. Solution for problem A1. First, let's sketch the free body diagram. Suppose that force F is big enough that this top wedge try to move up. It means that the force of friction will be going down, and the normal force is perpendicular to this surface. Now we can write equations. For horizontal motion we have 3ma equal force F minus force of friction, which is 3 mu mg. Also we can write equations for motion of this top wedge. For horizontal motion we have ma equal normal force sine theta plus force of friction cosine theta. And for vertical part we have normal force multiplied by cosine theta, that's equalized by gravity force mg plus force of friction F multiplied by sine theta. And in a critical case we have force of friction equal mu multiplied by normal force. And also we have from this first equation that acceleration equal force F over 3m minus mu g. Now we can put these expressions to our equations for motion of this top wedge. And we have these 2 equations. From the second equation we can express normal force, which is equal this expression. And now we can insert this expression here and finally find what is maximum possible force F. That will be this expression, and after some reductions we have this answer. This is answer for maximum possible force F. Let's do the same for minimum possible when this up wedge try to move down. In that case force of friction has opposite sign, and we can rewrite these equations. Now force of friction has opposite sign. This is why we have for motion of this top wedge these 2 expressions. And we do the same steps. Now when we insert force of friction mu n to these equations and acceleration, we have these 2 equations, and from this first equation again we can express what is normal force. That will be this expression. And the last step is to put this normal force here. And finally for force F we have this expression, which is solution for smallest possible force of F. That was a solution for problem A1. There is other way to solve this problem, and we can use a so-called non-inertial frame of reference. If we use a frame of reference which is moving to the left with acceleration a, we can use this dynamic with a non-inertial frame of reference. In this new frame of reference, this horizontal arrow, that's the acceleration a, which is going to the right. This vertical arrow, that's acceleration g. And the red arrow, it's a direction for net effective acceleration, which is going in this system. And now we see that effective angle will be theta minus this angle between red arrow and the vertical. And we have this expression for this angle. We have tangent phi equal a over g. And now we can find what is tangent for this effective angle, which is theta minus phi. So we have for tangent theta minus phi, that's equal this expression. But this tangent for critical acceleration equal mu, coefficient of friction. Mu equal this expression, and now we have tangent phi equal mu minimum over g, which is this expression. And this minimum acceleration we can use to find what is minimum force F. That's the approach for using non-inertial frame of reference. Same way we can find what is maximum possible acceleration and maximum possible force F. Now we have angle phi greater than theta, and we have maximum possible acceleration, and we have to find what is tangent phi minus theta, and that will be critical angle equal mu. And now tangent phi equal a maximum over g, which is this expression. And from here we can find what is maximum force F. That was a solution using non-inertial frame of reference. And also we can mention that if initially tangent theta less than mu, the minimum force equals 0, because we already not reached the critical angle.